This is the second lecture on Euler's phi function, and this lecture is meant for NET, SET, JL, junior lecturers, degree lecturer, aspirants. In the earlier video, the lecture 1 was devoted for the properties, some of the properties of Euler's phi function. In this lecture, lecture 2, we will state and prove two more results on Euler's phi function. Let phi of n be the cardinality of the set consisting of A belongs to n, the set of natural numbers, A less than n, and the GCD of A comma n is 1. That means phi of n is the Euler's phi function. Then, in the lecture 1, I have proved the result 1, there exists infinitely many n such that phi of n greater than phi of n plus 1. Second result I have proved, there exists infinitely many n such that phi of n less than phi of n plus 1. These are the two results what I have proved on the Euler's phi function in the lecture 1, which is already there in the YouTube. Interested viewers can watch that YouTube video. Now, the aim of this lecture is to prove the following two properties. Property 3, there exists n belongs to n such that n greater than, there exists a capital N belongs to the set of natural numbers such that capital N greater than 2, and for all n greater than capital N, phi of capital N is less than phi of n. And one more result, that is result 4. The set consisting of phi n by n, n belongs to n, has infinitely many limit points. We will prove this set has infinitely many limit points. So the aim is to prove these two properties of the phi n. Now we throw some light on Euler's phi function. Euler's phi function is also called Euler's torsion function, and it is also called a phi function. And it is a very important number theoretic function, and phi of n, where n is a positive integer greater than 1. So n is a positive integer greater than 1, then phi of n is defined as the number of positive integers less than n that are relatively prime to n. That is, for n belongs to n, the set of natural numbers n greater than 1, phi of n is the cardinality of the set consisting of m belongs to n, the set of natural numbers m less than n, and the GCD of m comma n is 1. And phi of 1 is defined as 1. Now, the following are the properties of phi of n. First one is n is prime if and only if phi of n is equal to n minus 1. Property 2, if n is not prime, then phi of n less than or equal to n minus 2, phi of n is less than n minus 1, phi of n less than n. So all these three are true. Property 3, if m and n are coprime, then phi of m into n, the product is equal to phi of m into phi of n. Result 4, that is property 4. If the prime factorization of n is given by n is equal to p1 to the power of m1, p2 to the power of m2, etc., pk to the power of mk, where p1, p2, pk are distinct primes, then phi of n is equal to n times 1 minus 1 by p1 into 1 minus 1 by p2 into etc. 1 minus 1 by pk. That is same as, and it is equivalent to phi of n is is equal to P1 to the power of M1 minus 1, P2 to the power of M2 minus 1, etc. Pk to the power of Mk minus 1 into P1 minus 1 into P2 minus 1 into Pk minus 1, and P1 minus 1 is phi of P1, this is phi of P2, this is phi of Pk also can be written, and this is an equivalent statement. And result 5, if P is a prime and P greater than 3, then we have proved phi of P minus 1 less than phi of P, and the other result is phi of P greater than phi of P plus 1 whenever P is a prime and P greater than 3. And in lecture 1, this property 1, result 2 I have proved, and the result 3 and result 4 are very famous results and whose proofs are very well known, and they are available in number theory textbooks. And the result 5 in lecture 1 I have proved using this, the property 1, that there exists infinitely many n such that phi of n is greater than phi of n plus 1. And the property 2, there exists finitely many n such that phi of n less than phi of n plus 1. So this is what we have done in L1. Now, in the present video, I will prove the properties 3 and 4 which I have shown in the beginning. Agreed. So, first we will prove the property 4. That is, the set consisting of phi n by n belongs to the set of natural numbers, has infinitely many limit points. Okay. Proof. Let P, capital P, be the set of all numbers phi of n by n belongs to the set of natural numbers. And phi of 1 by 1 is 1, phi of 2 by 2 is 1 by 2, phi of 3 by 3, that is 2 by 3, etc. And observe that for any natural number n, phi of n is strictly less than n and less than or equal to n, phi of n by n is less than or equal to 1. So note that P is an infinite set and 0 less than phi of n by n less than or equal to 1. That means P is a bounded infinite set. Therefore, we use the Bolzano-Weierstrass theorem. By Bolzano-Weierstrass theorem, P has a limit point. So now let P and Q be primes, and we will now prove that phi of Q by Q is a limit point of P for any given prime number Q. So now let epsilon greater than 0 be given. Then mod of phi of Q by Q minus phi of the product QP by QP is equal to mod of phi of Q by Q minus phi of QP, where P and Q are prime, so that will be phi of Q into phi of P and by Q into P. And we see that phi of Q by Q is common here, phi of Q by Q in brackets 1 minus phi of P by P. Phi of P is P minus 1 because P is a prime. P minus 1 by P is 1 minus 1 by P. So you will get phi of Q by Q in brackets 1 minus in bracket 1 minus 1 by P, 1 cancels, and we are left with phi of Q by Q into 1 by P. We can make it less than epsilon for all primes P greater than 1 by epsilon into Q by phi of Q. Agreed? Agreed. So it tells you what? It tells you what? Every neighborhood of phi of Q by Q contains at least one point, phi of QP by QP. So what we have proved is, this shows that every neighborhood of phi of Q by Q contains an element phi of QP by QP, an element of capital P, where P is chosen like this, that is P is greater than this 1 by epsilon into Q by phi of Q. So this shows that every neighborhood of this contains at least one more point other than this when P is chosen like this. That means phi of Q by Q is a limit point for each given prime Q. So So because Q can be chosen in infinitely many ways, the set capital P has infinitely many limit points, hence the result. So that proves our property 4, the set consisting of phi n by n, n belongs to n, has infinitely many limit points. This is the property. This is the property of this set. We now proceed for the next result, that is 3. Property 3 is there exists a capital N belongs to n such that n greater than 2, and for all n small n greater than capital N, phi of n is less than phi of small n. Okay. To prove this result, we need 2 more results. Before that, we use the following 2 results which are very, very trivial. First one is, if P is an odd prime, then phi of P is equal to P minus 1. When P is an odd, P minus 1 is even. Correct. Phi of P is equal to P minus 1 is even. Now the second property is, if P is prime greater than or equal to 5, then phi of P, the Euler's P function of the P, where P is a prime greater than or equal to 5, is greater than or equal to 4. This is a very, very easy to see this one, and it's a good property. So phi of Euler's P function of 5 is 5 minus 1 4, phi of 7 minus 1 6, phi of 11 minus 1 10. So we are considering all primes greater than or equal to 5. So what we see is 4 is equal to phi of 5 less than phi of 7 less than phi of 11 less than etc. This means phi of P is greater than or equal to 4 when P is a prime greater than or equal to 5. That's this property. Is a very easy property, very easy to see, and this property we require in our due course. Okay, we want a result 7 to prove the property 3. If n greater than 2, then phi of n is even. Let the prime factorization of that n is p1 to the power of m1 into p2 to the power of m2, etc. pk to the power of mk greater than 2, where p1, p2, pk are distinct primes. Now phi of n, we know this formula, p1 to the power of m1 minus 1, p2 to the power of m2 minus 1, etc. into pk to the power of mk minus 1 into p1 minus 1 into p2 minus 1 into pk minus 1, and p1 minus 1 is phi of p1, p2 minus 1 is phi of p2, pk minus 1 is phi of pk. That we write here. Agreed. So that is phi of n. We continue in the next slide. This is the brought forward, and when n greater than 2, when n has this prime factorization, then phi of n is this. Agreed. Now, what are the possibilities for n? N may be even or n may be odd. So when n is even, suppose that n is even, n greater than 2, n is even, n greater than 2, then n will be of the form 2 power m1 into p2 to the power of m2, etc. into pk to the power of mk greater than 2, where each pi 2 less than or equal to I less than or equal to n is an odd prime. Is an odd prime. That means prime bigger than or equal to 3. Is an odd prime because 2 has already come. And what are the, when n is even, then 2 is the only factor, that is 2 without any power. 2, only 2 is a factor of n. That's the first possibility. The second possibility is some 2 power m1 where m1 greater than or equal to 1. So that is 2 square, 2 cube, so on and so forth. They may be factors. So phi of n will be 2 power m1 minus 1 into p2 to the power of m2 minus 1 into pk to the power of mk minus 1 into phi of 2 into phi of p2 and phi of pk, and phi of 2 is 1. Now, if m1 is 1, that means just 2 is a factor. 2. That is 2 power 0, 2 power, see, just m1 is 1, that is 2, just 2 is a factor. Then phi of n is equal to this one, and 2 to the power of m1 minus 1, where m1 is equal to 1, that will be 2 power 0, that is 1, phi of 2 is 1, so you are left with only this much. Now when m1 is 1, if you go there, 2 power m1, and this p2, pk, etc., each pi is an odd prime. Now phi of n is this much, phi of 2, etc., this is even. This is phi of n is even, because since phi of pi is even. Agreed. If m1 is greater than or equal to 2, that means the higher powers of 2, then phi of n will be 2 power m1 minus 1 into p2 to the power of m2 minus 1 into pk to the power of mk minus 1 into phi of p2, etc. Phi of pk is even. This is even. Why? Because 2 power m1 minus 1 is even when m1 greater than or equal to 2. We are not, this argument doesn't depend on these p2, pk, what are they. But in the earlier case, when m1 is equal to 1, when n greater than 2, and when m1 is equal to 1, these p2s are odd primes. So this is the case. So that means these two cover that when n is even, phi of n, when n is even, phi of n is even. Second case, suppose that n is odd, where n greater than 2, then n, the prime factorization will be p1 to the power of m1 into p2 to the power of m2 into etc. pk to the power of mk, where each of these pi, I is equal to 1 to n, all of them, they are odd primes. And we have phi of n is this expression, yes, and phi of, what are these p1, p2, pk? They are odd primes. When pi is an odd prime, phi of pi is pi minus 1 is even. So phi of n is even since each phi of pi is even. Okay, so that's the case, and clubbing these two cases, we get if n greater than 2, then phi of n is even, hence the result, and this is a good result. So remember this result, if n greater than 2, then phi of n is even. Now, we are trying to prove this property 3, and we need one more result, that is result 8. Phi of n is equal to 2. That means for what values of n, phi of n is 2. This proves if and only if n is equal to 3 or 4 or 6. And if n is equal to 3, phi of 3 is 3 minus 1, 2, right? And if n is 4, phi of 4 is 4 into 1 minus 1 by 2, that is again 2. And when n is 6, it is phi of 2 into 3, that is phi of 2 into phi of 3, phi of 2 is 1, phi of 3 is 2. So again 2. So that means it is very straight to see that if n is equal to 3 or 4 or 6, then phi of n is 2. Agreed. What about the converse? Conversely, let us suppose n is a number of the form 2 power alpha, 3 power beta, the first two primes, and multiplied by p1 to the power of m1 into p2 to the power of m2 into pk to the power of mk, where p1, p2, pk are distinct primes, and each prime number pi in this greater than or equal to 5, because we have already taken 2 and 3, and the next prime will be, so each pi is a prime greater than or equal to 5. Now, in the converse part, 2 is equal to phi of n, that is phi of this expression, that is 2 power alpha minus 1, 3 power beta minus 1, p1 to the power of m1, p2 to the power of m2 minus 1, pk to the power of mk minus 1 into phi of 2, phi of 3, phi of p1, phi of p2, etc., phi of pk. Yes. and phi of 2 value is 1 and phi of 3 value is 2. So 2 power alpha minus 1, 3 into beta to the beta, 3 to 3 power beta minus 1, etc. multiplied by, and phi of 2 is 1, we are not written, phi of 3 is 2, and etc. Now 2 multiplied by 2 to the power of alpha minus 1 will be equal to 2 is equal to 2 power alpha minus 1 into 2 power alpha, 3 power beta minus 1, etc. The remaining things as it is. Let's call this as the equation 1. Equation 1. Agreed. Suppose that at least one of these MIs, suppose at least one of these MIs is greater than or equal to 1, where I is equal to 1 to n, 1, 2, 3 up to n. Suppose P1, that is P1 to the power of m1 minus 1. So m1 is greater than or equal to 1. When m1 is greater than or equal to 1, now, and phi of P1, what is P1? P1 is a prime greater than or equal to 5. When P is a prime greater than or equal to 5, phi of P1 will be greater than or equal to 4. And thereby the right hand side becomes bigger than 4, whereas the left hand side is just 2. So we recall, if P is a prime greater than or equal to 5, then phi of P is greater than or equal to 4. Then phi of Pi is, because one of the Mi is greater than or equal to 1, then phi of Pi is greater than or equal to 4, and the right hand side 1, this exceeds 2, therefore it's a contradiction because its left hand side is 2. It now follows that none of these MIs greater than or equal to 1. For any of these I is equal to 1 to k, Mi is not greater than or equal to 1. Therefore, each Mi is 0 for all I is equal to 1 to k, and thereby your n reduces to 2 power alpha into 3 power beta for some non-negative integers alpha and beta. Alpha and beta. We continue in the next slide. We are trying to establish the property 3. From the last slide, we have n is equal to 2 power alpha into 3 power beta for some non-negative integer alpha and beta, and phi of n is equal to 2. Therefore, 2 is equal to phi of n, right? And that will be phi of 2 power alpha into 3 power beta, that is phi of 2 power alpha into phi of 3 power beta. And now let us see, phi of, from this what I can see is phi of 2 power alpha is 2 and phi of 3 power beta is 1. That is 1. Or phi of 2 power alpha is 1 and phi of 3 power beta is 2. So these are the two possibilities. And phi of 2 power alpha is equal to 2 means 2 power alpha minus 1 is equal to 2. Phi of 3 power beta is 1. This is possible when beta is 0. Or phi of 3 power beta is 3 power beta minus 1 into phi of 3. Phi of 3 is 2. 2 into 3 to the power of beta minus 1 is equal to 2. Phi of 2 power alpha is 1. This is possible when alpha is 0 or alpha is equal to 1. When alpha is 0, phi of 1 is 1. When alpha is 1, phi of 2 is 1. Agreed. So this will imply 2 power alpha minus 1 is equal to 2 means alpha is equal to 2, beta is equal to 0, or 2 into 3 power beta minus 1 is equal to 2. This is possible when beta is equal to 1, alpha is equal to 0, or alpha is equal to 1. Thus we have alpha is equal to 2, beta is equal to 0, or beta is equal to 1, alpha is equal to 0, or beta is equal to 1, alpha is equal to 1. This will imply n is equal to 2 power alpha, 3 power beta. That will be 2 square, that is equal to 4. n is equal to 2 power alpha, 3 power beta. For these values, n is equal to 3. And for these values, n is equal to 2 power alpha into 3 power beta will become 2 power 1 into 3 power 1 is, that is 2 into 3, that is equal to 6. Thus what we have proved is phi of n is equal to 2 implies n is equal to 3 or n is equal to 4 or n is equal to 6. This is the converse part of that result. Therefore, phi of n is equal to 2 if and only if n is equal to 3 or 4 or 6, hence the result. Equivalently, suppose the n is greater than 6, then phi of n is not equal to 2. So equivalently, phi of n is not equal to 2 if and only if n greater than 6. Agreed? Now we are ready to establish the property 3. There exists n belongs to n such that capital N belongs to natural numbers such that capital N is greater than 2, and for all n greater than capital N, phi of capital N is less than phi of n. What is that capital N? Right. Proof. If we take n greater than 6, then phi of n is even. Why? You see the result 7. If n greater than 2, phi of n is even. So, n is greater than 2, phi of n is even. So, n greater than 6, phi of n is even. Agreed. And when n greater than 6, phi of n not equal to 2. What is the result? Result 8 says phi of n is 2 if and only if n is equal to 3 or 4 or 6. So, phi of n not equal to 2 means n greater than 6. So, because n greater than 6, phi of n not equal to 2. Thus, phi of n is not equal to 2 means phi of n is bigger than 2. And phi of 6 is 2. So, phi of n is greater than phi of 6 for all n greater than 6. So, phi of n is greater than phi of 6 for all n greater than 6. That is, phi of 6 is less than phi of n for all n greater than 6. So, that is, there exists a capital N is equal to 6, belongs to a set of natural numbers such that n greater than 2, such that phi of n is less than phi of capital N is less than phi of small n for all n greater than capital N. So that capital N, there exists that capital N is 6 and satisfying this property, hence the result. So thus the property 3 is proved. Thus we have proved the two properties what I have stated, 3 and 4. Those stated properties I have established. Right. Now let us look at a question that is asked, that has appeared in the CSIR National Eligibility Test held on 26th November 2020, and the question is from section B. The problem is, let phi of n be the cardinality of this set, that is phi of n is a Euler's V function, then which of the following is not true? So the property 1 and the property 2, which I have established, proved in lecture 1, and 3, there exists n belongs to n such that n greater than 2 for all n greater than capital N, phi of capital N is less than phi of n. This is the property 3 which I have established in this lecture. And the property 4, the set phi of n by n belongs to n has finitely many limit points is the one option given to us, but whereas I have proved this set has infinitely many limit points, that is my property 4. So therefore, the options 1, 2, 3 are true, and the option 4 is not true. So therefore, the options 1, 2, 3 are true, and the option 4 is not true. The option 4 is not true because in the option 4, it is given this set has finitely many limit points, but this set has infinitely many limit points, which we have shown in the property 4. Therefore, our answer is the option 4 is not true. So that is the solution of this problem that is given in the National Eligibility Test held on 26th November 2020. It is from the section B. And I am sure that you have understood and liked the proofs of the properties 3 and 4 in this lecture. I am sure that you have liked the proofs and work out some of the theoretical aspects of the Euler's phi function in your study. I wish you all the best. Thank you.